It was April 23rd, 1992. George Smoot stood in front of a room of his peers at an American Physical Society meeting. For years, he and his team had been working with data from the Cosmic Background Explorer satellite, or COBE. The satellite was staring at the oldest light in the universe, a faint, cold glow left over from the Big Bang. Since its discovery in 1965, this light had appeared perfectly uniform, a smooth, featureless wall of radiation coming from every direction. It was too perfect. A perfectly smooth early universe could not explain the lumpy universe we see today. The galaxies, the clusters of galaxies, the great walls and voids of the cosmos, none of it should exist if the beginning was completely uniform. There had to be some kind of imperfection, some seeds from which all this structure could grow. The COBE team had been searching for those seeds. They spent years analyzing the satellite's data, trying to filter out the noise from our own galaxy and solar system. They were looking for tiny temperature differences in that ancient light, and they found them. And Smoot put an image on the screen. It was an oval map of the entire sky, colored in blotches of blue and red. The colors represented minuscule variations in temperature. Red spots were slightly warmer. Blue spots were slightly cooler. The differences were incredibly small, just 1 part in 100,000. It was like measuring the height of a sand dune on a surface the size of the United States and finding it was only a few centimeters tall. But that was enough. Those tiny fluctuations were exactly what they were looking for. They were the primordial seeds, the gravitational wells and hills of the infant universe. The places where matter would begin to clump together, eventually forming everything we know. The room was stunned into silence, then erupted in applause. John Mather, the project's lead scientist, had already presented the team's other major finding that the background radiation perfectly matched the theoretical spectrum of a hot, dense early universe. But Smoot's map was the visual proof. It was the baby picture of the universe. At the press conference later, Smoot said, "If you're religious, it's like looking at God." It was a moment that changed cosmology forever. The Nobel Prize came in 2006 for both Mather and Smoot. That single map, born from years of painstaking work, began a golden age of cosmology, turning a field of speculation into a precision science. Number 24, we live in the aftermath of a sound wave. The early universe was filled with a plasma so dense that light couldn't travel freely. The sound speed in this primordial soup was immense, about 57% the speed of light. Any disturbance in this plasma would create sound waves, just like a rock dropped in a pond creates ripples. These weren't sound waves you could hear, of course. They were waves of pressure and density. These waves, called baryon acoustic oscillations, rippled through the hot, dense plasma for about 380,000 years. The universe was a battleground between gravity and pressure. Gravity, fueled by dark matter, tried to pull everything into clumps. But the photons, the particles of light, were trapped with the normal matter, creating an immense outward pressure. This pressure pushed back against gravity. So a dense spot would pull matter in, get hotter and denser until the radiation pressure became too strong and pushed it all back out. This created an expanding shell of matter and light, a sound wave moving outward from the initial dense spot. This process happened everywhere, all at once, creating countless overlapping sound waves. Then, at about 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine and form the first hydrogen atoms. This event is called recombination. Suddenly, the photons were free. They were no longer stuck to the matter. They could now travel unimpeded through space. This is the light we see today as the cosmic microwave background. When the photons were set free, the sound waves stopped dead in their tracks. They froze in place. This left a faint imprint on the universe. Each sound wave left behind a shell of slightly denser matter at the point where it stopped. The size of these shells was fixed. They had a specific radius, determined by how far a sound wave could travel in 380,000 years. That distance works out to about 490,000 light years at the time of recombination. As the universe expanded, this distance expanded with it. Today, that characteristic distance is about 500 million light years. This means that if you pick any galaxy, you are slightly more likely to find another galaxy 500 million light years away than at other distances. You know, it's a very subtle effect, a preference of just about 1%. You know, scientists didn't just see this in the CMB. They looked for it in the distribution of galaxies. In 2005, two independent teams of astronomers announced they had found this 500 million light-year signature in maps of millions of galaxies. It was a stunning confirmation of the model. The pattern of galaxies in the modern universe matched the pattern of sound waves in the infant universe. This gives us a standard ruler. We know the physical size of that sound wave pattern in the early universe. By measuring its apparent size in the sky today, we can measure the distance to those galaxies and the expansion history of the universe. This has become one of our most powerful tools for studying dark energy, the mysterious force causing the universe's expansion to accelerate. The sound of the Big Bang is still echoing, not as sound, but in the very placement of galaxies across the cosmos. Number 23. The universe has a definitive birthday. The age of the universe was a source of great debate for much of the 20th century. Estimates varied wildly, from as young as 10 billion years to as old as 20 billion. A major problem arose in the 1990s when some calculations for the age of the universe came out younger than the oldest stars we could see. This was a logical impossibility. You can't have stars that are older than the universe they live in. This paradox highlighted how uncertain our cosmic measurements were. The cosmic microwave background provided the key to solving this. The CMB is not just a single picture. It contains a huge amount of information encoded in the size of its hot and cold spots. By studying the patterns in the CMB map, cosmologists can build a precise model of the universe. This model, known as the lambda CDM model, describes a universe filled with dark energy lambda and cold dark matter CDM, along with the normal matter we are familiar with. The model works like this. You input a set of cosmic parameters, like the density of different types of matter and energy, and the initial conditions. Then you run a simulation to see what kind of CMB pattern this universe would produce after 13.8 billion years of evolution. You then compare the simulated pattern to the real pattern observed by satellites like MAP and Planck. By adjusting the input parameters, you can find the best possible fit. The process is a bit like tuning a radio. You know, you twist the dials until the signal comes in perfectly clear. One of the most important dials in this model is the age of the universe. The age directly influences how much the universe has expanded, which in turn affects the apparent size of the features in the CMB. For instance, the characteristic size of the sound waves frozen into the CMB at 380,000 years acts as a fixed ruler. By measuring the angular size of these features on the sky today and knowing their actual physical size back then, we can calculate the distance the light has traveled. This calculation depends critically on the expansion rate and the overall age. The Planck satellite, which operated from 2009 to 2013, gave us the most precise data yet. After years of analysis, the Planck team released their results. The best fit model gave an age for the universe of 13.799 billion years, with an uncertainty of just 21 million years. This is an incredible level of precision. It's like knowing the age of a 40-year-old person down to the nearest couple of months. This age resolved the paradox of the old stars. The oldest stars found in globular clusters are now estimated to be around 13.5 billion years old. This fits comfortably within the age of the universe. The CMB didn't just give us a number. It gave us a number we could trust, derived from the physics of the very early universe, and it brought consistency to our understanding of cosmic history. We now have a definitive birth certificate for our cosmos. Number 22. The universe is almost perfectly smooth. The temperature of the cosmic microwave background is 2.725 Kelvin. That's just 2.725 degrees above absolute zero. What's truly remarkable is that this temperature is the same everywhere you look, to an astonishing degree of accuracy. The hot and cold spots that George Smoot's team discovered are deviations of only about 18 microkelvin. That's a change of 1 part in 100,000. To put that into perspective, if the Earth were this smooth, the highest mountain would be about 80 meters tall and the deepest ocean trench would be similarly shallow. The entire planet would be almost a perfect sphere. This extreme uniformity is known as the cosmological principle. It's the idea that on large scales, the universe is homogeneous, the same everywhere, and isotropic, the same in all directions. The CMB is the best evidence we have for this principle, but this smoothness presented a huge problem for cosmologists. It's called the horizon problem. Let's look at 2 opposite points in the sky. The light from one point has taken 13.8 billion years to reach us. The light from the opposite point has also taken 13.8 billion years. This means the total distance between those 2 points is almost 28 billion light years. In the early universe, these 2 regions were even farther apart relative to the size of the universe then. According to the standard Big Bang model, there was no time for these 2 regions to ever have been in contact. They could never have exchanged heat or information, so how did they end up at the exact same temperature? It would be like finding 2 people on opposite sides of the Earth who have never met, but their body temperatures are identical down to 100,000th of a degree. It's statistically impossible. The solution came in 1981 from a physicist named Alan Guth. He proposed a theory called cosmic inflation. The idea is that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated exponential expansion. It grew from a size smaller than a proton to something larger than a grapefruit in about 10, raised to the power of 32 seconds. Inflation solves the horizon problem elegantly. Before this rapid expansion, the entire region that would become our observable universe was a tiny subatomic patch. This patch was small enough to have been in thermal contact and to have reached a uniform temperature. Inflation then stretched this tiny, smooth region to an enormous size. The smoothness we see in the CMB today is a magnified view of the smoothness that existed in that initial tiny patch. So the CMB's incredible uniformity is not a puzzle anymore. It's a key piece of evidence for inflation. The universe isn't smooth by chance. It was ironed flat during the most violent expansionary phase of its existence. The tiny fluctuations we see are the other side of the coin. They were quantum fluctuations in that initial tiny patch, stretched to cosmic scales by inflation. The CMB tells us the universe started incredibly simple smooth, with tiny quantum ripples. Number 21, the first atoms were forged everywhere at once. For the first 380,000 years of its existence, the universe was an opaque fog. It was too hot for neutral atoms to exist. It was a sea of free-roaming protons, electrons, and photons. The photons were constantly scattering off the free electrons like light in a thick fog. They couldn't travel more than a short distance before being deflected. This is why we cannot see light from any earlier period. The universe was opaque. This period is called the plasma epoch. During this time, the universe was constantly expanding and cooling. Eventually, the temperature dropped to about 3,000 Kelvin. This was a critical threshold. At this temperature, the protons and electrons no longer had enough energy to resist their mutual attraction. They began to combine to form the first stable, neutral hydrogen atoms. This process is called recombination. The term is a bit of a misnomer since they were never combined before, but it has stuck. This event did not happen in one specific place. It happened everywhere across the entire cosmos at roughly the same time. As soon as a neutral hydrogen atom formed, it was much harder for a photon to interact with it. The universe, which had been a dense fog, suddenly became transparent. The photons that were present at that exact moment were now free to travel through space in straight lines forever. These are the photons that make up the cosmic microwave background. They have been traveling for 13.8 billion years. They are a snapshot of the moment the universe became transparent. When we look at the CMB, we are literally looking at the light from this surface of last scattering. It's not a physical surface, but rather a spherical shell in time surrounding us. It's the point in the past where the universe transitioned from opaque to transparent. The CMB light was originally very energetic, corresponding to the 3000 Kelvin temperature of the plasma. It would have been a bright yellowish orange glow in all directions. But as the universe has expanded over the last 13.8 billion years, it has stretched the wavelengths of these photons. This is called cosmological redshift. The light has been stretched by a factor of about 1,100. This has shifted it from the visible spectrum all the way down into the microwave part of the electromagnetic spectrum. Its temperature dropped from 3000 K to the 2.725 K we measure today. So the CMB is not just a relic. It is a direct photograph of the moment the first atoms formed. It tells us about the physical conditions of the universe at that time. The sharpness of the transition from opaque to transparent, which we can measure in the CMB data, tells us how quickly recombination happened. It's a baby picture of the universe taken when it was just 0.0027% of its current age. Number 20, most of the universe is missing. For centuries, astronomers thought the universe was made of the same stuff we are: atoms, stars, planets, gas, and dust. Everything we could see. In the latter half of the 20th century, evidence began to mount that this was not the whole story. There was a lot more out there than meets the eye. The cosmic microwave background turned this the suspicion into a hard fact and gave us the precise recipe for the cosmos. The pattern of hot and cold spots in the CMB is incredibly sensitive to what the universe is made of. The exact size and strength of these spots depend on the cosmic ingredients. Think of it like a bell. The sound a bell makes depends on its size, shape, and the material it's made from. In the same way, the sound of the early universe recorded in the CMB depends on the cosmic composition. Let's look at the ingredients. First, there's normal matter, or baryonic matter. This is everything made of protons and neutrons: us, the Earth, the Sun, all the galaxies. Then there's dark matter. This is a mysterious substance that does not interact with light. We know it's there because of its gravitational effects on galaxies and galaxy clusters. Finally, there's dark energy, a strange form of energy inherent to space itself that is causing the expansion of the universe to accelerate. The CMB allows us to measure the proportions of these three ingredients with stunning precision. Here's how. The first and most prominent peak in the CMB's power spectrum, a graph showing the strength of fluctuations at different angular sizes, tells us about the overall geometry of the universe. The relative heights of the odd and even peaks tell us about the amount of normal matter versus dark matter. The baryons, or normal matter, were coupled to the photons and felt the radiation pressure. Dark matter, on the other hand, did not. It only felt gravity. So, when a clump of matter started to form, the dark matter just stayed put at the center of the gravitational well. The normal matter, however, was pushed back out by the photon pressure, creating those sound waves. This difference in behavior leaves a distinct signature in the CMB power spectrum. The more normal matter there is, the stronger the compression of the sound waves, which enhances the odd-numbered peaks, the first, third, etc., over the even-numbered ones. By precisely measuring these peaks with satellites like WMAP and Planck, scientists were able to read the cosmic recipe. The result was a shock. Normal matter, the stuff of our existence, makes up only about 4.9% of the total energy and matter density of the universe. Your dark matter accounts for about 26.8%. The vast majority, a staggering 68.3%, is dark energy. This means that for every one part of the universe we can see and understand, there are about 5 parts of a mysterious, invisible matter we can't detect directly, and about 14 parts of a mysterious energy we don't understand at all. Over 95% of the cosmos is unknown to us. The CMB didn't just hint at this, it wrote it down in black and white, giving us the exact humbling proportions. Number 19, the universe's geometry is flat. Is the universe flat, open, or closed? This is one of the most fundamental questions in cosmology. It's a question about the overall shape of space-time. A flat universe is the one we're familiar with from Euclidean geometry. Parallel lines stay parallel forever, and the angles of a triangle add up to 180 degrees. In a closed universe, which has positive curvature like the surface of a sphere, parallel lines would eventually converge, and the angles of a triangle would add up to more than 180 degrees. If you traveled in a straight line long enough, you would end up back where you started. In an open universe, which has negative curvature like the surface of a saddle, parallel lines would diverge, and the angles of a triangle would add up to, less than 180 degrees. The fate of the universe is tied to its geometry. A closed universe has enough mass and energy to eventually halt its expansion and collapse back on itself in a big crunch. An open or flat universe would expand forever. The key parameter that determines the geometry is the total density of matter and energy in the cosmos. If the density is above a certain critical density, the universe is closed. If it's below, it's open. If it's exactly at the critical density, the universe is flat. The cosmic microwave background provides a direct way to measure this. The CMB acts as a giant backdrop to the universe. We know the physical size of the sound waves in the early universe when the CMB was released. The most common size of the hot and cold spots in the CMB corresponds to the distance a sound wave could travel before recombination. This is our standard ruler. Now, imagine drawing a triangle on this backdrop, with the long side being the size of one of these sound wave features. We can measure the angular size this feature appears to have in the sky today. If the universe is flat, the light from the ends of that feature will travel in straight lines to us, and the angular size will be what we expect from simple geometry. If the universe is closed, positively curved, space-time would act like a magnifying lens, and the spots would appear larger than expected. If the universe is open, negatively curved, space-time would act like a demagnifying lens, and the spots would appear smaller. The first major peak in the CMB power spectrum corresponds to this characteristic angular size. Satellites like MAP and Planck have measured the position of this peak with incredible precision. The result is unambiguous. The peak is exactly where it should be for a flat universe. The measurement from the Planck satellite found the universe to be flat to within an error of just 0.4%. This is a profound result. It means the total energy density of the universe is astonishingly close to the critical density. This flatness is also a key prediction of the theory of cosmic inflation. Inflation would have stretched any initial curvature of the universe to such an enormous scale that our observable patch would appear perfectly flat, just as a small patch on the surface of the Earth appears flat to us. The CMB, once again, provides powerful evidence for inflation and tells us that, on the largest scales, the geometry we learned in school is the one that governs the cosmos. Number 18, inflation really happened. The theory of cosmic inflation is one of the pillars of modern cosmology. It proposes that the universe underwent a phase of extreme exponential expansion in the first 10 raised to the power of 32 seconds of its existence. It was proposed in the early 1980s to solve some major problems with the standard Big Bang model, like the horizon problem, why is the CMB so smooth, and the flatness problem, why is the universe's density so close to the critical density. The CMB has provided the strongest evidence that this incredible event actually occurred. First, as already mentioned, the CMB confirms two of inflation's major predictions: the universe is almost perfectly smooth, and it is geometrically flat. Inflation explains both of these by taking a tiny, smooth, causally connected patch of space and stretching it to a colossal size. Any initial curvature would be stretched out to flatness, but inflation makes other, more specific predictions that have also been verified by the CMB. Inflation predicts that the tiny fluctuations on top of the smooth background should have a particular character. These fluctuations originated as tiny quantum jitters in the primordial vacuum. Inflation grabbed these quantum fluctuations and stretched them to astronomical scales. These became the seeds of all structure in the universe. The theory predicts that these fluctuations should be adiabatic, meaning all types of matter, normal and dark and energy, fluctuate together. It also predicts that the fluctuations should be nearly scale invariant. This means the ripples have roughly the same strength on all different physical scales. It's like a noise signal where the volume is the same for low-pitched and high-pitched sounds. However, inflation also predicts a slight deviation from perfect scale invariance. The fluctuations should be very slightly stronger on larger scales than on smaller scales. This is measured by a parameter called the spectral index. Perfect scale invariance would have a spectral index of 1. Inflation predicts a value slightly less than 1. The Planck satellite measured this spectral index with extreme precision. The result was 0.965 with a very small error bar. This is a powerful confirmation of inflation. It's not exactly 1, just as the theory predicted. This rules out simpler alternative theories and provides strong support for the inflationary paradigm. Furthermore, inflation predicts that the fluctuations should follow a Gaussian or bell curve distribution. This means that large deviations from the average temperature should be very rare, following a specific statistical pattern. The CMB fluctuations follow this pattern almost perfectly. The search is now on for the smoking gun of inflation, a specific type of polarization in the CMB called primordial B modes. These would be a signature of gravitational waves produced during the violent inflationary expansion. Detecting these is incredibly difficult, and while there have been some tantalizing hints, a definitive detection has not yet been made. But the evidence we already have from the CMB's temperature map alone, its flatness, smoothness, and the specific nature of its fluctuations map, makes a very strong case that the universe we live in is the product of an inflationary past. Number 17, we can see the universe's first light being bent. Einstein's theory of general relativity tells us that mass warps the fabric of spacetime. A massive object, like a star or a galaxy, creates a gravitational well. Light, as it travels through the universe, follows these curves in spacetime. This means that the path of light can be bent by massive objects. This phenomenon is called gravitational lensing. We see it all the time when the light from a distant galaxy is distorted into arcs and multiple images by a closer galaxy cluster that lies in the line of sight. The light from the cosmic microwave background is no exception. It has been traveling for 13.8 billion years. On its long journey to us, it has passed through and around all the cosmic structures that have formed in the intervening time galaxies, clusters of galaxies, and the vast filaments of dark matter that make up the cosmic web. All of this mass has slightly deflected the paths of the CMB photons. This means that the CMB map we see today is a slightly distorted version of the original. The light from a hotspot might be slightly shifted from its original position, or its shape might be slightly stretched. The effect is very subtle, typically deflecting the light by just a few arc minutes, a fraction of a degree. But with the high-resolution maps from, satellites like Planck, these tiny distortions can be measured statistically. Scientists can do this by looking for specific non-Gaussian patterns in the CMB. While the primordial CMB is very nearly a perfect Gaussian field, the lensing effect introduces subtle correlations between different parts of the sky. By analyzing these correlations, cosmologists can reconstruct a map of all the matter that the CMB light has passed through. This is an incredibly powerful tool. It allows us to create a map of the distribution of all matter, both normal and dark, throughout the entire observable universe. Since dark matter makes up the vast majority of matter, this is essentially a map of the dark matter scaffolding of the cosmos. These maps of the CMB lensing effect show the great filaments and knots of the cosmic web, confirming our models of structure formation. This lensing map also provides an independent way to check our cosmological model. The amount of lensing we observe depends on the amount of matter in the universe and how it is clustered. The measured lensing signal matches the predictions of the standard lambda CDM model beautifully. It also helps to break degeneracies between different cosmological parameters, making our overall measurements more precise. And for example, it gives us an independent way to constrain the mass of neutrinos, as massive neutrinos would slightly smooth out the cosmic structure, reducing the lensing effect. The CMB is not just a static baby picture, it's a dynamic probe that carries the imprint of 13.8 billion years of cosmic evolution. Number 16, the universe is lumpy, but only just. The 1992 COBE discovery of temperature fluctuations in the CMB was revolutionary. It showed that the early universe wasn't perfectly smooth. It had tiny density variation. These were the seeds from which all cosmic structures, from stars to superclusters of galaxies, eventually grew. Here's how it worked. In the early plasma, a region that was slightly denser than average had a slightly stronger gravitational pull. This region would be a gravitational well. As photons climbed out of this well to travel towards us, they would lose some energy. This loss of energy corresponds to a slight cooling, a process called the Sachs-Wolf effect. So the slightly denser regions in the early universe appear as cold spots in the CMB map today. Conversely, less dense regions or gravitational hills would cause photons to gain energy, appearing as hotspots. So the blue and red blotches on the CMB map are a direct representation of the primordial density fluctuations. Blue, cooler spots are the places where matter was starting to clump together. These were the seeds of future galaxies and clusters. The red, hotter spots were the seeds of the great cosmic voids, the vast empty spaces between galaxy clusters. The scale of these fluctuations is what's important. They were, on average, just 1 part in 100,000. If they had been much smaller, say 1 part in a million, gravity would not have been strong enough to pull matter together against the universe's expansion. No structures would have formed. The universe would be a cold, uniform, and lifeless soup of gas. If the fluctuations had been much larger, say 1 part in 1,000, the universe would be a much more violent and chaotic place. Gravity would have been so overwhelmingly strong that matter would have collapsed very quickly into massive black holes. It's unlikely that stable galaxies and stars like our sun could have formed in such a universe. The just right amplitude of these fluctuations is a profound clue about the universe's origin. The theory of cosmic inflation provides a natural explanation for this. During inflation, tiny quantum fluctuations in the vacuum of space were stretched to macroscopic sizes. The amplitude of these fluctuations is related to the energy scale at which inflation occurred. The observed amplitude in the CMB suggests that inflation happened at an incredibly high energy, far beyond anything we can replicate in particle accelerators on Earth. By studying the statistical properties of these lumps and bumps in the CMB, we can learn about the fundamental physics of the very early universe. The CMB map is not just a map of temperature, it's a map of the initial conditions of our entire cosmos. It tells us that our universe of intricate structures grew from the tiniest, most subtle of quantum beginnings. Number 15. We know when the first stars switched on. After the universe became transparent at 380,000 years, it entered a period known as the Cosmic Dark Ages. There were no stars and no galaxies yet. The universe was filled with a neutral hydrogen and helium gas, slowly clumping together in the gravitational wells laid down by dark matter. The only light was the fading glow of the cosmic microwave background. This period lasted for hundreds of millions of years. Eventually, in the densest regions, the gas collapsed enough to form the very first stars. These were not like the stars we see today. They were likely hundreds of times more massive than our sun, made of pure hydrogen and helium. They lived fast and died young, burning incredibly hot and bright. The intense ultraviolet light from these first stars began to ionize the neutral hydrogen gas around them, stripping the electrons from the protons once again. This process is called reionization. First, individual bubbles of ionized gas formed around the first stars and galaxies. As more and more stars switched on, these bubbles grew and merged until eventually all the gas in the intergalactic medium was reionized. The cosmic dark ages ended, and the cosmic dawn began. The cosmic microwave background gives us a way to pinpoint when this happened. The CMB photons have been traveling towards us ever since recombination. As they pass through the universe during the epoch of reionization, some of them would have scattered off the newly freed electrons. This scattering process leaves a subtle but detectable imprint on the CMB. Specifically, it affects the polarization of the CMB light. The polarization is the direction in which the light wave oscillates. The scattering during reionization produces a large-scale polarization signal in the CMB. By measuring the strength of this signal, we can calculate how many CMB photons were scattered. This, in turn, tells us how many free electrons there were, and therefore, when reionization happened. The more scattering, the earlier reionization must have started. This is a very difficult measurement to make. The signal is faint and is spread out over large angular scales on the sky, but the MAP and Planck satellites were able to measure it. The data suggests that reionization was a complex process. It likely started around 400 million years after the Big Bang and was largely complete by the time the universe was about 1 billion years old. This is a crucial piece of our cosmic history. It marks the transition from the simple, dark, early universe to the complex, luminous universe of galaxies we see today. The CMB acts like a backlight, and by seeing how much of that light has been scattered, we can learn about the fog of reionization that stood between us and the CMB. It allows us to see the collective glow of the first stars, not as individual points of light, but through their effect on the oldest light in the universe. Number 14, the universe obeys the simplest rules. One of the most striking features of the CMB is its simplicity. The patterns of hot and cold spots can be described by a surprisingly small set of numbers. This is the core of the Lambda CDM model, the standard model of cosmology. This model is defined by just 6 key parameters. With only these 6 numbers, we can generate a simulated CMB that is statistically almost indistinguishable from the real one observed by the Planck satellite. These 6 parameters are the density of baryonic normal matter, the density of cold, dark matter, the age of the universe, or a related parameter, the Hubble constant, the optical depth to reionization, which tells us when the first stars formed, and 2 numbers that describe the primordial fluctuation. These 2 numbers are the amplitude of the fluctuations, how lumpy the universe was, and the spectral index, how the lumpiness changes with scale. That's it. Just 6 numbers. These 6 values, when plugged into the equations of general relativity and our understanding of physics, can describe the universe from when it was a fraction of a second old to the present day. They predict the large-scale structure of galaxies, the abundance of light elements like hydrogen and helium, the accelerating expansion of the universe, and, of course, the detailed statistical properties of the CMB. The fact that such a simple model works so well is a profound statement about the nature of the universe. It suggests that the initial conditions of the cosmos were incredibly simple. The universe did not start with some complex, arbitrary set of conditions. It started with a nearly uniform state, with tiny random fluctuations that have a very simple statistical description. All the complexity we see today, galaxies, stars, planets, life emerged from these simple beginnings, governed by the known laws of physics. The CMB is the ultimate proof of this. The data from the Planck satellite contains thousands of data points describing the CMB power spectrum. The fact that a 6-parameter model can fit these thousands of points with exquisite precision is a triumph of modern science. It's the cosmological equivalent of realizing that all the complexity of chemistry can be described by the periodic table and the rules of quantum mechanics. Of course, this simplicity is also a source of mystery. The model tells us the what, but not the why. It tells us we need dark matter and dark energy in specific amounts, but it doesn't tell us what they are. It tells us the initial fluctuations had a certain character consistent with inflation, but it doesn't tell us the detailed physics behind inflation. The success of this simple model gives cosmologists confidence that they are on the right track, but it also clearly delineates the next great frontiers of cosmic discovery, understanding the fundamental nature of these simple ingredients. Number 13, we can weigh the universe's neutrinos. Neutrinos are ghostly subatomic particles. They are incredibly abundant. Trillions of them are passing through your body every second. For a long time, they were thought to be massless. However, particle physics experiments in the late 1990s showed that neutrinos do have a small amount of mass, but these experiments could only measure the difference in mass between the different types of neutrinos, not their absolute mass. The cosmic microwave background provides a surprisingly sensitive way to weigh these elusive particles. In the very hot and dense early universe, neutrinos were in thermal equilibrium with everything else. They were created in vast numbers along with photons and other particles. As the universe expanded and cooled, the neutrinos decoupled from the primordial plasma when the universe was about 1 second old. They started to travel freely through the cosmos, creating a cosmic neutrino background, similar to the CMB but much harder to detect directly. Because neutrinos have mass, they travel at speeds slightly less than the speed of light. In the early universe, they were moving so fast they were relativistic, behaving much like light. But as the universe cooled, they slowed down. Today, they are moving relatively slowly. This has an effect on the formation of structure in the universe. Massive neutrinos, even with their tiny mass, contribute to the overall gravity of the universe. However, because they move so fast, they tend to smooth out density fluctuations on small scales. They can easily escape from smaller gravitational wells. This means that in a universe with more massive neutrinos, it would be harder for small structures like dwarf galaxies to form. The growth of cosmic structure would be slightly suppressed. This suppression of structure leaves a subtle imprint on the cosmic microwave background. It affects the CMB in two main ways. First, it slightly alters the pattern of the primary temperature fluctuation. Second, and more significantly, it affects the gravitational lensing of the CMB. A universe with more massive neutrinos would be slightly smoother, which would lead to a weaker gravitational lensing signal. The Planck satellite was able to measure the CMB lensing effect with high precision. By comparing the measured amount of lensing to the predictions from models with different neutrino masses, the Planck team was able to set an upper limit on the total mass of all three neutrino types. The latest results from Planck, combined with data from baryon acoustic oscillations, limit the sum of the neutrino masses to be less than 0.12 electron volts. This is an incredibly tiny mass, more than 4 million times smaller than the mass of an electron. This cosmological measurement is currently the tightest constraint we have on the neutrino mass. It's a remarkable example of how the largest scales in the universe can be used to probe the properties of the smallest known particles. The afterglow of the Big Bang is acting as a giant cosmic particle physics experiment. Number 12, an anomaly hints at a flaw in our model. The standard cosmological model, lambda CDM, is incredibly successful. It fits the CMB data with just 6 parameters. However, when you look at the CMB map in extreme detail, there are a few strange features anomalies that don't seem to fit the model perfectly. They are not statistically significant enough to cause a crisis, but they are tantalizing hints that something might be missing from our understanding. The most famous of these is the axis of evil, a name coined by cosmologists to reflect its unsettling nature. The issue relates to the largest scale fluctuations in the CMB. These are the hot and cold spots that cover huge patches of the sky. The standard model, based on inflation, predicts that these fluctuations should be random. There should be no preferred direction in the universe, but that's not what we see. When scientists analyze the largest features, they find that they seem to be aligned. The quadrupole and octupole moments, the technical names for the largest scale patterns, are not randomly oriented. They appear to be aligned with each other, and even more strangely, they seem to be aligned with the plane of our own solar system, the ecliptic plane. This is very odd. The CMB is coming from the farthest reaches of the universe. The solar system is a tiny local structure. There is no known physical reason why the largest features in the entire observable universe should be correlated with the orientation of our local planetary system. It could be a massive coincidence. The odds are low, maybe 1 in 10,000, but in science, such flukes can happen. Another possibility is that it's a subtle, undiscovered error in the data processing, some contamination from our own solar system that we haven't managed to remove. Another major anomaly is the cold spot. This is a particularly large and cold region in the CMB map, located in the constellation Eridanus. It's much larger and colder than would be expected from the random fluctuations predicted by the standard model. It's a significant outlier. One explanation is that it's just a statistical fluke A in any random map. You're bound to find some unusual features. Another more exotic explanation is that it's the signature of a supervoid, an enormous region of space between us and the CMB that is unusually empty of galaxies. Such a void would cause a slight cooling of the CMB light, passing through it via the integrated Sachs-Wolf effect. Astronomers have looked for such a void, and while there seems to be a deficit of galaxies in that direction, it's not clear if it's large or empty enough to explain the entire cold spot. These anomalies and a few others, like a strange difference in the CMB signal between the two hemispheres of the sky, continue to puzzle cosmologists. They could be statistical flukes that will disappear with better data, they could be subtle errors in our analysis, or they could be the first cracks in our standard model pointing towards new physics, a more complex inflationary history, or even a different overall geometry to the universe. For now, they remain intriguing mysteries written in the oldest light. Number 11, the steady state theory was disproven. Before the discovery of the CMB, there were two main competing theories for the origin and evolution of the universe. One was the Big Bang theory, which proposed that the universe began in an extremely hot, dense state, and has been expanding and cooling ever since. The other was the steady state theory, championed by astronomers Fred Hoyle, Hermann Bondi, and Thomas Gold. The steady state theory proposed that the universe was eternal and unchanging on the largest scales. Yes, it was expanding, and galaxies were moving apart from each other. But the theory suggested that new matter was continuously being created in the voids between galaxies. This new matter would then form new galaxies, so that the overall density and appearance of the universe would remain the same for all time. In this view, the universe had no beginning and no end. It was an elegant and philosophically appealing idea. But it made a clear prediction. If the universe is eternal and unchanging, it should not have a specific temperature. The Big Bang theory, on the other hand, made a very specific prediction. If the universe started in a hot, dense state, the radiation from that early fireball should still be detectable today. As the universe expanded, this radiation would have cooled down to just a few degrees above absolute zero, and it would fill all of space. In 1964, Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey, were working with a large horn antenna. They were trying to use it for satellite communication and radio astronomy, but they were plagued by a persistent, faint hiss of background noise. The noise was the same no matter where they pointed the antenna, day or night, all year round. They did everything they could think of to eliminate it. They checked all their electronics. They even cleaned out pigeon droppings from inside the antenna, thinking the bird's body heat might be the source. But the noise remained. It was a microwave signal with a temperature of about 3 Kelvin. At the same time, a team of physicists at nearby Princeton University, led by Robert Dick, were actively building an experiment to search for the predicted relic radiation from the Big Bang. They had calculated that it should have a temperature of a few Kelvin. When Penzias and Wilson heard about the Princeton group's work, they realized what they had found. Their persistent noise was not noise at all. It was the afterglow of creation. It was the cosmic microwave background. The discovery was a death blow for the steady-state theory. A universe that is the same for all time has no reason to be filled with a uniform thermal radiation bath at 2.7 Kelvin. The CMB was direct, irrefutable evidence that the universe had a hot, dense past. It had a beginning. Penzias and Wilson won the Nobel Prize in Physics in 1978 for their accidental but monumental discovery. The CMB fundamentally changed our view of the universe, replacing an eternal cosmos with one that has a dynamic and dramatic history. Number 10, we can directly see the fog of the early universe. The CMB provides us with a snapshot of the universe at 380,000 years old, but it also contains information about what happened before that. The key is in the polarization of the CMB light. Polarization refers to the orientation of the light wave's oscillation. Most light sources, like a light bulb, are unpolarized. The light waves oscillate in all directions randomly. But light can become polarized if it scatters off something. In the early universe, before recombination, the photons were constantly scattering off free electrons in the primordial plasma. This scattering process would have polarized the light. The specific pattern of this polarization is called an E-mode pattern. It has a specific curl-free mathematical property similar to the pattern of an electric field. The physics of this is straightforward. If a photon sees the plasma around it as perfectly uniform, any polarization it gets from scattering in one direction is canceled out by scattering from another direction. The net result is no polarization, but if the photon is in a region where the plasma is moving, for example, if it's at the crest or trough of one of the sound waves, it will see a non-uniform or anisotropic distribution of light. This temperature anisotropy in the plasma leads to a net polarization of the scattered light. This means that the polarization map of the CMB is directly linked to the motion of the plasma at the moment the CMB was released. The E-mode polarization signal is a direct tracer of the velocity of the primordial soup. When we map the E-modes, we are not just seeing a temperature map, we are seeing the dynamics of the early universe. We are directly observing the swirling, oscillating fog of the plasma epoch. The BICEP 2 experiment and later the Planck satellite have successfully mapped these E-mode polarization patterns. The results are in perfect agreement with the predictions of the standard cosmological model. The E-mode signal is exactly what you would expect from the sound waves that we see in the temperature map. This provides a powerful, independent check on our understanding of the early universe. It confirms that our picture of a hot, dense plasma filled with sound waves is correct. There is another, much more sought-after type of polarization called B-modes. These have a curly pattern, like a magnetic field. Primordial B-modes are not produced by the plasma dynamics. They can only be generated by gravitational waves. Finding primordial B-modes in the CMB would be direct evidence of gravitational waves from the inflationary epoch, the smoking gun of inflation. This search is ongoing, but the detection of the E-modes is already a major achievement. It has opened a new window onto the early universe, allowing us to go beyond a simple photograph and create a dynamic picture of the cosmic plasma in motion. Number 9. The universe's expansion rate is a source of tension. The Hubble constant, h0, is one of the most important numbers in cosmology. It tells us how fast the universe is expanding today. A higher value means a faster expansion and a younger universe. For decades, measuring the Hubble constant precisely has been a major goal for astronomers. There are two primary ways to measure it. One is the local method. This involves building a distance ladder Astronomers measure the distances to nearby galaxies using standard candles like Cepheid variable stars. Then, in those same galaxies, they find brighter standard candles like Type Ia supernovae, which can be seen much farther away. By calibrating the supernovae in the nearby galaxies, they can then use them to measure distances to very distant galaxies. By measuring the redshift, how fast they are moving away from us, and distance for many galaxies, they can calculate the expansion rate. The most precise measurements using this method from projects like SHOES using the Hubble Space Telescope give a value of about 73 kilometers per second per megaparsec. This means a galaxy 1 megaparsec, about 3.26 million light years away, is receding from us at 73 km/s. The second method uses the cosmic microwave background. The CMB provides a picture of the early universe. By using our standard cosmological model Lambda CDM, which has been so successful at describing the CMB's features, we can project forward and predict what the expansion rate should be today. This method relies on a thorough understanding of the physics of the early universe and the ingredients of the cosmos, dark matter, dark energy, etc. The Planck satellite's detailed measurements of the CMB, when fed into the Lambda CDM model, predict a Hubble constant of about 67.4 km/s MPC. And therein lies the problem. The two measurements disagree. 73 and 67.4 are not the same. And crucially, the uncertainties on these measurements are now so small that they do not overlap. The discrepancy is about 5 sigma, which in particle physics is the threshold for a new discovery. This is known as the Hubble tension. What could be the cause? It could be an unknown systematic error in one or both of the measurements. The local distance ladder is complex, and there could be subtle errors in the calibration of the standard candles. The CMB measurement is very clean, but it is model dependent. It assumes that the Lambda CDM model is a complete and correct description of the universe. If the discrepancy is real, it means there is something wrong with our standard cosmological model. We may need to add new physics to it. Perhaps there is a new type of relativistic particle in the early universe, sometimes called dark radiation. Or perhaps dark energy is not a constant, but changes over time. Another possibility is some new interaction in the dark matter sector. The Hubble tension is currently one of the most exciting and pressing problems in cosmology. It suggests that our beautifully simple 6-parameter model, which works so well for the CMB, might be incomplete. The CMB is not just confirming our theories, it is also pointing to potential new frontiers and revealing the subtle cracks in our current understanding of the cosmos. Number 8, we can find giant galaxy clusters by looking for shadows. The cosmic microwave background is not just a relic from the past. It's also a tool we can use to study the universe today. One of the most powerful ways it does this is through something called the Sunyaev-Zeldovich SZ effect. The galaxy clusters are the most massive gravitationally bound objects in the universe. They can contain hundreds or even thousands of galaxies. The space between these galaxies is not empty. It's filled with a very hot, tenuous gas, a plasma with temperatures of 10 to 100 million Kelvin. When the ancient photons of the CMB travel through one of these massive galaxy clusters on their way to us, they interact with the hot, high-energy electrons in this intracluster gas. The electrons give the photons a tiny energy boost through a process called inverse Compton scattering. This shifts the CMB photons to slightly higher frequencies or shorter wavelengths. This means that if we look at the CMB in the direction of a galaxy cluster, we will see a slight distortion in its blackbody spectrum. At lower frequencies, longer wavelengths, where the CMB signal is normally rising, we will see a deficit of photons. The cluster casts a shadow on the CMB. At higher frequencies, where the signal is falling, we will see an excess of photons. There is a specific Newell frequency where the effect is zero, around 217 GHz. The great thing about the SZ effect is that its strength does not depend on the distance to the galaxy cluster. A shadow is a shadow. This makes it an incredibly powerful tool for finding galaxy clusters, especially very distant ones that would be too faint to see with optical telescopes. Telescopes like the South Pole Telescope and the Atacama Cosmology Telescope are designed to scan large areas of the sky at microwave frequencies, specifically looking for these SZ signatures. They have discovered thousands of previously unknown galaxy clusters this way. By studying the number and distribution of these clusters at different distances, and therefore at different times in cosmic history, we can learn about the growth of structure in the universe. The formation of massive clusters is very sensitive to cosmological parameters, particularly the amount of dark matter and dark energy. The population of SZ-detected clusters provides an independent way to measure these parameters and test our standard model. The CMB, acting as a backlight for the entire universe, allows us to find the largest structures in the cosmos simply by looking for the tiny shadows they cast. Number 7. The universe reached a state of maximum entropy. The second law of thermodynamics states that the entropy, or disorder, of a closed system always increases. The early universe was an incredibly low entropy state. All the energy was concentrated in a hot, dense, and relatively uniform plasma. The existence of gravity allowed for this low entropy state to evolve into the high entropy, structured universe we see today, with stars and galaxies representing a clumping of matter and a huge increase in overall entropy. The cosmic microwave background represents a unique moment in this story. It is a near-perfect blackbody radiation field. A blackbody is a theoretical object that absorbs all radiation that hits it, and when in thermal equilibrium emits radiation in a characteristic spectrum that depends only on its temperature. This blackbody spectrum is the most thermally random state that radiation can be in. It represents the maximum possible entropy for a photon gas at a given temperature. In the early universe, the constant scattering between photons and matter ensured that the radiation field reached a state of perfect thermal equilibrium. The photons and matter were tightly coupled, sharing the same temperature. When the universe became transparent at recombination, the photons were released, but they kept this blackbody spectrum. The expansion of the universe has since cooled the radiation down, but it has preserved its perfect blackbody shape. In the early 1990s, the FIRUS instrument on the COBE satellite, led by John Mather, measured the spectrum of the CMB with incredible precision. The data points fell perfectly on the theoretical blackbody curve. It was the most perfect blackbody spectrum ever measured in nature. The fit was so good that the error bars on the data points were smaller than the thickness of the line drawn for the theoretical curve on the graph. This is a profound result. It is the ultimate proof that the universe began in a hot, dense thermal state. No other theory besides the Big Bang can naturally explain the existence of such a perfect blackbody radiation field filling all of space. The steady-state model, for example, would have starlight being absorbed and re-radiated by dust. But this would create a spectrum with many bumps and wiggles from atomic and molecular lines, not a smooth, perfect blackbody. The CMB's perfect thermal spectrum tells us that the early universe was, in a very real sense, simple and boring. It had reached a state of maximum thermal disorder. It was this simple, high entropy radiation bath coupled with the low entropy state of matter under gravity that set the stage for the emergence of all the complexity we see today. Number 6. The universe does not appear to be spinning. Is the universe rotating? It's a fundamental question. General relativity allows for solutions that involve a rotating universe. If the universe as a whole had some net angular momentum, it would have observable consequences. We would not see the same universe in all directions. There would be a preferred axis of rotation. A rotating universe would leave a distinct fingerprint on the cosmic microwave background. The CMB photons would be slightly Doppler shifted, depending on their direction relative to the axis of rotation. This would create a large-scale spiral pattern, or a quadrupole temperature anisotropy in the CMB map. The temperature of the CMB would appear to vary systematically across the sky in a way that reflects this rotation. The scientists have searched for such a pattern in the high-precision maps from MAP and Planck. They have looked for any evidence of a large-scale, non-random pattern that could be attributed to cosmic rotation. The result of these searches is a resounding null. There is no detectable sign of rotation. The data from the Planck satellite allows us to put very tight constraints on how fast the universe could possibly be rotating. The limits are incredibly stringent. If the universe is rotating, it is doing so at a rate of less than 1 degree per 10 billion years. It is, for all intents and purposes, perfectly still. This finding provides strong support for the cosmological principle, the idea that the universe is isotropic, the same in all directions on large scales. A rotating universe would violate isotropy. The fact that we don't see any rotation is another piece of evidence that the simple assumptions underlying our standard cosmological model are correct. This doesn't mean that individual objects within the universe, like galaxies and galaxy clusters, don't rotate. They do. The angular momentum of these objects is thought to have arisen from tidal torques and interactions during the process of structure formation. But on the whole, the universe itself seems to have no net spin. The initial conditions of the Big Bang appear to have been non-rotating, adding to the picture of an incredibly simple beginning. Number 5, the universe's contents were revealed by a specific light polarization. We've discussed how E-mode polarization in the CMB confirms our model of sound waves in the early universe. But the polarization signal does more than that. It helps us break degeneracies between different cosmological parameters, allowing us to pin them down with much greater certainty than we could with the temperature map alone. One of the most important examples of this is the relationship between the optical depth to reionization, a measure of when the first stars turned on, and the amplitude of the primordial fluctuation. In the CMB temperature map, these two parameters have a similar effect. A universe with a higher fluctuation amplitude would produce stronger hot and cold spots. But a universe that was reionized earlier, a higher optical depth, would have more of its primary CMB signal washed out by scattering, which would damp the fluctuations on small scales. It's possible to get a similar looking temperature map by increasing one of these parameters and decreasing the other. This makes it hard to measure either of them precisely using temperature alone. This is where polarization comes in. The scattering of CMB photons during reionization produces a very specific polarization signal on large angular scales. This reionization bump in the polarization power spectrum is directly proportional to the optical depth. It is not affected by the initial amplitude of the fluctuations, so by measuring the polarization of the CMB, we can get a direct, independent measurement of when reionization happened. The WMAP and Planck satellites did exactly this. Once you have a precise value for the optical depth from the polarization data, you can plug that back into your analysis of the temperature data. This breaks the degeneracy. You can no longer trade one parameter off against the other. This allows you to determine the primordial fluctuation amplitude with much higher precision. This is just one example. The detailed structure of the polarization power spectrum, particularly the locations and heights of its peaks and troughs, provides a wealth of information that is complementary to the temperature data. The phase of the polarization peaks relative to the temperature peaks, for example, provides a powerful confirmation that the fluctuations we see are adiabatic and originated before the CMB was formed, as predicted by inflation. Essentially, the CMB gives us two views of the early universe, the temperature map and the polarization map. By combining these two views, we can create a much sharper, more robust, three-dimensional picture of our cosmic origins and measure the fundamental parameters of our universe with unprecedented accuracy. Number 4, we have detected the faint glow of galaxy clusters. The integrated Sachs-Wolf ISW effect is one of the most subtle and difficult to measure features in the cosmic microwave background. It provides a direct probe of the influence of dark energy on the growth of cosmic structures. Here's how it works. We know that CMB photons gain energy becoming hotter or bluer when they fall into a gravitational well, like the one created by a large supercluster of galaxies. They then lose that energy as they climb back out. In a universe without dark energy, where the expansion is decelerating due to matter, the gravitational well of a supercluster would become slightly deeper while the photon is passing through it. The photon would have to climb out of a slightly stronger well than the one it fell into, so it would lose a little extra energy, resulting in a net cooling. However, we live in a universe dominated by dark energy. Dark energy is causing the expansion of the universe to accelerate. This acceleration has a strange effect on large gravitational structures. It causes them to stretch and flatten out. Their gravitational wells become shallower over time. Now, consider a CMB photon passing through a supercluster in our dark energy-dominated universe. It falls into the gravitational well and gains energy. While it is passing through, the well is stretched and made shallower by cosmic acceleration. So, when the photon climbs out, it doesn't have to work as hard, it loses less energy than it gained. The net result is that the photon comes out with slightly more energy than it had when it went in. It is slightly blue-shifted, and the CMB in that direction appears slightly hotter. This effect is called the late-time integrated Sachs-Wolf effect. It only happens when the universe's expansion is not dominated by matter, that is, when dark energy has taken over. This means that by looking for this effect, we are directly seeing the influence of dark energy on the cosmic web. The effect is incredibly small, a tiny temperature shift on top of the primary CMB fluctuations. It's impossible to see by looking at a single supercluster, but it can be detected statistically. Scientists do this by taking a map of the large-scale structure of the nearby universe from galaxy surveys and cross-correlating it with the CMB temperature map. They check to see if the CMB is, on average, slightly hotter in the directions of large superclusters and slightly colder in the directions of large voids. This cross-correlation has been detected. The signal is weak, but it is statistically significant. The first detections were made in 2003 using WMAP data and various galaxy catalogs, and the result has been confirmed with higher significance using Planck data and more extensive galaxy surveys. This detection of the ISW effect is one of the most direct pieces of evidence we have for the existence of dark energy independent of supernova data or baryon acoustic oscillations. It shows us the subtle glow of the cosmic web, illuminated by dark energy's relentless push. Number 3, primordial gravitational waves remain elusive. The theory of inflation doesn't just predict the temperature fluctuations we see in the CMB. It also makes another, more profound prediction, the production of a background of gravitational waves. The incredibly violent, accelerated expansion of inflation would have shaken the very fabric of space-time, creating ripples that would propagate through the universe forever. These are primordial gravitational waves. These gravitational waves would be far too faint to be detected by instruments like LIGO, which are sensitive to high-frequency waves from merging black holes. But they would have left a unique imprint on the cosmic microwave background. As these gravitational waves stretched and squeezed space-time, they would have induced a specific type of curly polarization pattern in the CMB, known as B modes. Detecting these primordial B modes is considered the ultimate smoking gun for inflation. It would be direct evidence of quantum gravity in action in the first moments of the universe. It would also allow us to measure the energy scale at which inflation occurred, giving us a window into physics at energies 1 trillion times higher than anything achievable at the Large Hadron Collider. The search for these B modes is one of the most intense and challenging quests in modern cosmology. The signal is expected to be incredibly faint, buried under a much larger B-mode signal that is generated by the gravitational lensing of the CMB by large-scale structures. This lensing effect takes the primary E mode polarization and twists some of it into B modes, creating a foreground that must be carefully modeled and removed. There is also a foreground of polarized dust emission from our own Milky Way galaxy. In 2014, the BICEP 2 experiment at the South Pole announced a detection of primordial B modes. The news caused a massive stir in the physics community. However, further analysis, especially using data from the Planck satellite, showed that the signal they saw was almost entirely due to polarized dust in our galaxy, not primordial gravitational waves. Since then, a host of experiments BICEP Keck Array, SPIDER, Polar Bear, ACT, SPT have been pushing the limits of sensitivity, slowly tightening the constraints on how strong the primordial gravitational wave signal can be. So far, nothing has been definitively detected. This doesn't mean inflation is wrong. Many models of inflation predict a signal that is below the current detection threshold. The quest continues. The next generation of CMB experiments like the Simons Observatory and CMB-S4 are being built with the express purpose of hunting for this faint polarized signal. A definitive detection of primordial B modes would be a monumental Nobel Prize-worthy discovery. Their non-detection so far is also valuable information, ruling out entire classes of inflationary models. The CMB's polarization remains our best hope for peering into the very first instant of time. Number 2. The universe confirmed general relativity. The cosmic microwave background is not just a test of cosmological models, it's a test of the fundamental theory of gravity itself, Einstein's general relativity. The entire framework we use to interpret the CMB, how fluctuations grow, how light travels, how the universe expands is built on the foundation of general relativity. The fact that our models fit the CMB data so perfectly is in itself a powerful confirmation of Einstein's theory on the largest possible scales. The CMB tests general relativity in several specific ways. The gravitational lensing of the CMB, for example, is a direct consequence of the way mass warps spacetime as described by GR. The amount of lensing we observe in the Planck data matches the predictions of GR with incredible precision. Scientists can use this to test for any deviations from GR. For example, some alternative theories of gravity predict that the way light is deflected by mass, as seen in lensing, should be different from the way mass affects the growth of structure. The CMB data, when combined with data from galaxy surveys, shows that these two effects are consistent with each other, just as GR predicts. The relationship between the temperature anisotropies and the E-mode polarization is another sharp test. In the standard model based on GR, these two patterns are not independent. The physics of the primordial plasma dictates a very specific correlation between them. The observed cross-correlation between the temperature and polarization maps matches the theoretical prediction perfectly. Any deviation would point to a breakdown of our understanding of the physics of the early universe, which is deeply intertwined with GR. Even the overall picture is a test. You know, the way the peaks in the CMB power spectrum are arranged like their positions, heights, and spacing is a direct consequence of how a plasma behaves under the influence of gravity in an expanding spacetime described by GR. The success of the model in fitting these features with just a few parameters is a testament to the power and accuracy of Einstein's theory over cosmic distances and across cosmic time. While there are still mysteries like dark energy and dark matter, the CMB shows us that the gravitational framework we use to describe the universe is remarkably successful. It has passed every test the CMB has thrown at it. Alternative theories of gravity are highly constrained by the CMB data. They must not only explain the accelerating universe, but also reproduce all the detailed features of the CMB that general relativity explains so naturally. So far, no alternative theory has been able to do this as elegantly or as successfully. Number 1, the universe had a beginning. Perhaps the most astonishing and fundamental thing the cosmic microwave background has taught us is the most simple. The universe had a beginning. Before the discovery of the CMB in 1965, it was scientifically plausible to believe in an eternal, unchanging universe, as described by the steady-state theory. This idea had a long philosophical history, the notion of a cosmos that had always existed and always would. The discovery of a faint thermal glow of microwaves coming from every direction in the sky changed everything. This radiation was not coming from stars or galaxies, it was coming from the fabric of space itself. Its perfect thermal blackbody spectrum was the unmistakable signature of a universe that was once in a state of thermal equilibrium, a state that was incredibly hot and incredibly dense. A static, eternal universe has no reason to be filled with the afterglow of a primordial fireball. The CMB is the echo of a creation event. It is a direct relic of a time when the entire observable universe was compressed into a volume smaller than a marble at a temperature of trillions of degrees. Every subsequent observation of the CMB has only strengthened this conclusion. The COBE satellite confirmed its perfect blackbody spectrum, proving its hot thermal origin. Then COBE, MAP, and Planck mapped its tiny temperature fluctuations. These fluctuations tell a consistent story. They are the quantum seeds planted in the first moments of time and stretched by inflation, which grew under the influence of gravity in an expanding universe to form all the structures we see today. The detailed physics encoded in those fluctuations, the sound waves, the polarization patterns, the statistical properties, all fit perfectly into a single coherent historical narrative. And it's a narrative that starts 13.8 billion years ago with the Big Bang. The cosmic microwave background transformed cosmology from a field of speculative ideas into a precision science. It allows us to take the universe's temperature, to determine its age, to take an inventory of its contents, to determine its geometry, and to piece together its history. It gives us a baby picture of the cosmos, showing a beginning that was remarkably simple, smooth, and governed by physical laws we can understand. It is the most profound archaeological artifact in existence, a message from the dawn of time that tells us unequivocally that our universe has a story and that we are a part of it.